System analysis using Laplace transforms. I told you earlier that what is the condition for causality? What is the condition for causality in terms of impulse response? Causality or physical realizability?
H of t is equals to 0 where t greater than 0.
Nice, correct. So the condition for causality is h of t equal to 0 for t less than 0. So this is the condition for causality. Okay. I hope all of you remember this.
Yes, sir.
Right. Now, shall we write the condition for BI stability? I didn't explain this in the classroom. Condition for BI stability. Can anyone tell me what do you mean by BI stable?
Bounded input and bounded outputs.
Correct. So when we have a system which is applied with an input x of t, which is bounded, and if you get the system output as also bounded, then the system is said to be bounded input, bounded output, stable. This is what we have learned earlier regarding the BIB stability. Now, what we now know is any system can be represented by its impulse response. Then what will be the output, or how can I calculate the output?
X of t convolution h of t.
Nice. It is convolution between input and the impulse response. Okay. So this condition for causality or physical realizability, this we have already seen earlier in the classes. And now we will go for writing the condition for BAB stability in terms of the impulse response, just like this. Now, the basic part or the assumption what we are going to do is x of t is already bounded. So I am taking the assumption that because I am checking for bounded input, bounded output stability, I am assuming that x of t is already bounded. What do you mean by boundedness? Is it time bounded or value bounded? What do you mean by bounded? A function is bounded means is it time bounded or value bounded here?
Time bounded, sir.
Hmm. Bounded input, is that I'm talking about time bounded? I think it's no. I'm talking about its value bounded. It's not about time bounded. It's all about value bounded. Example, u of t. U of t values lies in between 0 and 1. So these are the bounds of u of t. Am I right?
Yes, sir.
So this is a value boundedness. So bounded input means the values of the signal should be bounded. It is not about time bound. I hope I made it clear again. It is value boundedness. Similarly, I can quote one more example. Sin t. Sin t value lies in between
Minus
minus
1
1
to
and
1.
1. Okay, that means it oscillates between, if I'm writing modulus, then I can write minus. Value lies into minus 1. Or I can write it as mod sin t minus 1. And right? I can also write like this. So this is also value bounded. Okay. So the thing I am talking about here is x of t is already bounded. Means it is not time bounded, it is value bounded. You can also observe here that u of t, the time range lies in between 0 and infinity. Whereas in this case of sin t, it is over the infinite limits. Okay. So the time is infinite bounded, but the signal values are value bounded. So bounded signal means it is only value bounded, not the time bounded. I am making this clear once again. So just like the condition here we are getting for causality and physical visibility as h of t equal to 0 for t less than 0, we will go for deriving the condition for BIB stability in terms of impulse response. Now, what I assumed here, so assumption is that x of t is already x of t is value bounded. That means we are giving this x of t as an input, which is already bounded. So I am giving bounded input. Okay. Now that boundedness of x of t, I am writing like this. What do you mean by this? What do you mean by this?
X of t is in between minus m to m.
Right. And its value is, and that m is finite. I am treating like that. Okay. Now, based on the output of an LTE system, y of t should be x of t convolution by impulse response. And since it satisfies the commutative property, I am going to write like this h of t convolution x of t since it is satisfying the commutative property. Now, can you please tell me y of t now? Integral infinite limits h of tau x of t minus tau theta. Is this clear which I have told now?
Yes, sir. Yes, sir.
Okay.
Yes.
So when can I say that the system is satisfying behavioral stability? Only when y of t is bounded. X of t bounded is already I assume. If you can check for the boundedness of y of t and it satisfies, then we can say that the system is behavioral stability. So now I need to check for the boundedness of this y of t. So what I do here is I am going to apply modulus for this y of t on both sides. So now what this becomes mod h of tau and this will be approximately equal to not directly equal to because I am taking that modulus inside into x of t minus tau. Till this point it is clear?
Yes, sir.
Okay. Now,
Sir,
yeah,
so once can you explain why you specifically taken mod?
because see here, I am talking about the boundedness values of u of t. Here, did you see these examples?
Yes, sir.
Okay. So the values of any function are generally represented as like modulus symbol like this. The sine t, its values are represented with mod or lying limit less than or equal to 1. In this fashion or in this form, which I represented here as sine t, I am writing here x of t like this. Till this point, is this clear?
Yes.
Okay. So x of t is bounded means I'm representing that statement in a mathematical form like this. Now what I am doing, I am now checking whether the output is bounded or not. That's the reason I am representing the values of y of t with this modulus. So the reason for applying the modulus is because we are checking the value boundedness of y of t. Okay.
Yes, sir.
Yeah. Now, what is a maximum value that x of t can reach?
M.
It is m, no? So what I'm doing is, for making this simple, I'm replacing this mod x of t. Now I have a question. Question is, I have already told that the values of x of t are bounded in between the finite m. Now tell me, if I shift this signal, does its bound change or it will remain the same?
It will remain the same.
It will remain the same because even though if u of t is lying in between 0 and 1, u of t minus 1 also lies in between 0 and 1 only. The values bound doesn't change, just time bound will be changed. So what I'm doing is, since here I have mod x of t minus tau and its bounds will be always m here even after shifting. I am replacing this mod x of t minus tau with its maximum bound. Then what I can do, what I can write, I can't remain this equality here. Then it becomes less than or equal to mod h of tau, and this I am replacing with m. Clear till this point?
Yes, sir.
Now,
Yes, sir.
this m is a constant, so I am taking that m out of the integral m. And can you please write the remaining? It is minus infinite infinite mod h of tau theta. Now, this can be observed as a product of two terms. One is a constant term, and the other one is the integral term. Okay. Now, for this mod y of t to be bounded, some m1, or I can write some n. What should be the condition? Already m is a finite value. This is finite. What is the other quantity that should become finite?
Integral, sir.
Integral. So that should become finite. So when this, since m is already finite, if this integral is also finite, the product of two finite values will result a finite value. So therefore, from this, the condition deduced for BI-BO stability in terms of impulse response is minus infinite infinite mod it, and earlier we wrote tau. I am writing in general now in terms of t dt. Finite means, how can I write that finiteness of this integral?
Less than infinity.
Less than infinity. So this is a condition for any system for being BI-BO stable. Now, can anyone tell me in words this statement? In words. In words. What is h of t?
Impulse function.
Impulse response of the system. Okay. Impulse response should be, because you have a mod, absolutely, I think you know this actually. And integration should result a value of finite, which is less than infinity. So which I write it as. You remember this statement? Function should
Yes,
be
sir.
absolutely integrable. So the condition for BI-BO stability for any LTI system is its impulse response should be absolutely integrable. Now, summarizing this, the condition for causality is impulse response h of t should be equal to 0 for t less than 0. This is causality or physical realizability. And then the condition for BI-BO stability is impulse response should be absolutely integrable. This is clear.
Yes,
Yes.
sir.
Now I want from you, from your side, I want a condition so that the system is both causal and BI-BO stable. Can anyone tell condition for a system to get satisfying both causality and BI-BO stability? You have the clue on the screen itself. Just you have to combine these two and tell me what can I write. Think about h of t. Not getting idea? You can respond, no problem. If you're not getting idea, I'll tell you. Shall I proceed?
Yes, sir.
Yeah, please check here. What are the limits for behavior stability?
Infinite limits.
Okay, it is infinite, minus infinite, plus infinite. Now see the condition for causality Is it this h of t existing for negative time?
No, sir.
Now combine these two and tell me.
So it's integral from 0 to infinity
Uh,
mod h of t dt less than infinity.
this is the condition. Since h of t is 0 for t less than 0, and that can be applied in the second one. Therefore, h of t will not have the negative limits. It will be from 0 to infinite mod h of t dt is less than infinite. This is the condition for causality and behavior stability. Clear?
Yes, sir.
Yes, sir.
Okay. So we will have a continuation for this in the next class. So the continuation is the condition we wrote now for causality or physical reversibility, behavior stability, and both causality and stability in terms of impulse response. Okay. In the next class, what we will do is we will write the condition in terms of, because we have the knowledge of Laplace transforms now. So Laplace transforms can be used for commenting on the nature of systems. This I have already mentioned. That is bilateral. You already wrote. You can check your book. Bilateral Laplace transform application is commenting on the nature of systems. So using this Laplace transform concept, we will again discuss about the same three conditions, and it's not in terms of h of t because I am talking about the Laplace transform. It will be in terms of ROC. That means for causal system, how the ROC should be. For BAB was stable, how the ROC should be. For I can say both causality and stability, how the ROC should be. So we will be discussing the ROC of H of S. Can anyone tell me what is H of S here? What is H of S here? And what is H of T here? Waiting for your reply.
The H of T is impulse response in time domain.
Right? Impulse response. Okay. And H of S. Do you remember this?
Yes, sir.
Transfer function which we represent in which domain? S domain. Because I am talking about Laplace transforms, we represent that in S domain. Okay. Now, let's talk about causality or physical realism. Now, just recollecting the condition that h of t should be equal to 0 for t less than 0. Now, based on the condition what I wrote here, can you please tell me whether the signal or the impulse response h of t is right-sided or left-sided?
Right side. Sir.
So, since h of t is 0 for t less than 0, h of t will be right-sided. Good, right-sided. And since I am talking about systems, h of s, the transfer function, will have the ratio y of s to x of s, which is a rational form. Am I correct till this point?
Yes, sir.
Yeah. So now I want to recollect a property of ROC. One of the property of ROC. If you have that in your book, please check once. That is, if the signal x of t is, so this is one of the property of ROC, property of ROC. If x of t is right-sided and x of s is rational, then how the ROC will be?
Right of rightmost pole.
Nice. ROC will be right of the rightmost pole. Rightmost pole. Nice. So based on the property which I have recollected, just make sure that I am rewriting this again, and in place of x of t we have h of t, and in place of x of s we have the transfer function h of s. Now I am rewriting the property. If the impulse response h of t is right-sided and the transfer function h of s is rational, then the ROC is, or ROC will be, right of the rightmost pole. Is it clear?
Yes, sir.
So for a system, now I'm saying that system is represented by its transfer function. For a system h of s to be causal or physically realizable, how the ROC should be? The ROC should be right of the rightmost pole. So this is what the conclusion we derive from these properties of ROC and the impulse response condition we have seen earlier. So once you have the information about the transfer function h of s, then check its ROC. If the ROC is right of the rightmost pole, then we say that that system is causal or physically realizable. Can I give one example for this?
Yes, sir.
Okay. Now see, I'm going to write a transfer function of, as an example, having some two poles. The two poles are s minus 2 and s plus 3. So now tell me, what are the pole locations for this?
2 comma minus 3.
S equal to 2 and s equal to minus 3. And if we represent that in the s plane, let me show the locations of poles. One is s equal to 2. So this is 1, this is 2, this is minus 1, minus 2, minus 3. So we have a pole at s equal to 2. We have a pole at s equal to minus 3. Then generally what we do, we draw a dashed line at the pole locations first. Then talking about right of the rightmost pole case, then tell me what will be the ROC in this case? What should be the causal ROC in this case?
2 to infinity, sir.
So among these two poles, pole 1 and pole 2, the rightmost pole is pole 2. That's why the ROC should be right of the rightmost pole. This is of from 2 to infinite. The ROC will be defined. Clear? Is this clear? The first property?
Yes, sir.
Yeah. Now we will go for the second one. What is the second condition? It is for BIBO stability. It is for BIBO stability. And that condition for BIBO stability, we wrote that earlier in terms of impulse response, is the impulse response should be absolutely integrable. Impulse response should be absolutely integrable. Now, the same condition, just like we wrote the condition in terms of impulse response and explain how the RBC should be for such a causal physical reversible system. Now we should talk about the same in terms of RBC for the condition of bounded output stability. Now, just I want to know, or I want to recollect the condition for convergence of the Laplace transform. Can anyone Laplace transform? Can anyone recollect it? Condition, the convergence depends on what? Is it real part of S or imaginary part of S?
Real part of it, sir.
Yeah. And the condition we wrote earlier is h of t into e power of minus sigma t dt should be less than infinite. Do you remember this condition? Maybe I can recollect that from this again. This is how we write the transfer function in terms of Laplace transform formula. Later we replace s with sigma plus j omega. We'll have it is h of t e power of minus sigma t e power of minus j omega t dt. And then talking about the finiteness, we apply the modulus on both sides. Now this can be written because equality doesn't hold good when the order of operations were interchanged. So mod comes inside, mod h of t e power of minus sigma t e power of minus j omega t dt. Now this modulus can be represented as mod h of t e power of minus sigma t into mod e power of minus j omega t dt. Now, what is the value of mod e power of minus j omega t?
1, sir.
It is 1. So therefore, the condition is mod h of t minus sigma dt. And for this h of s to be finite, this integral should be finite. So for this h of s to be finite, the resultant integral should be finite. That is how the condition arrived like this. H of t mod e power of minus sigma t dt. Should be infinite, should be finite means it should be written as less than infinite. Now understood how this condition has got for the Laplace transform for convergence,
Yes, sir.
and it depends only on the sigma. Right. Now I want you to compare this condition and this condition and tell me what has been done for the exponential, or what is the value of sigma here to get this one.
Sigma equal to 0.
So in this condition, When I make sigma equal to 0, then e power of minus sigma t, that is e power of 0, becomes 1, and this condition is reduced. Okay, so when sigma is equal to 0, in this condition is written as mod h of t dt is region, which is already discussed about that this is a condition for BI stability. That means when I substitute sigma equal to 0, I am getting this. That means in the ROC, therefore, what is the conclusion from this? In the ROC, the line sigma equal to 0 should be present. What is the another name for sigma equal to 0 line?
Imaginary axis.
Right. So the conclusion from this is when the ROC of h of s contains imaginary axis, then we say that, so final conclusion is when the ROC of the system transfer function contains the imaginary axis, that is sigma equal to 0 line, then the system is BI stable. Any doubts till this point?
No, sir.
Right. Now let's see an example for this. Example. Let me write. Okay. H of t equal to. I am directly giving the impulse response of some system e power of minus 2t u of t. Okay. Now, can anyone tell me what is the transfer function? H of s. Transfer function is just apply the Laplace transform.
1 by s plus 2.
Right. 1 by s plus 2. And what will be the ROC?
Sigma greater than minus 2.
Sigma greater than minus 2. Now let me plot this in the S plane. Real axis, imaginary axis. So see it as S plane. When you have a real pole at s equal to minus 2, you have a real pole. So I'm representing that pole location here. And as how we write like this. Now you can see that ROC is sigma greater than minus 2. Sigma greater than minus 2, like this. Now what is the range of sigma here in this case?
minus 2 to infinity.
Minus 2 to infinity. Now see whether the line sigma equal to 0 or imaginary axis is present in the ROC or not.
Yes, sir, it's present.
Right. So sigma equal to 0 line is included in the ROC. Therefore, as per the earlier discussion, what is the conclusion of h of s equal to 1 by s plus 2, what I wrote here for the ROC sigma greater than minus 2 is, what is the conclusion is?
BIBO stable.
BI was stable. Now I will give one more example. H of t equal to minus a power of minus 3t u of minus t. Now tell me, what is h of s in this case?
1 by s plus 3.
1 by s plus 3. And tell me what is the ROC?
Sigma less than minus 3.
Sigma less than minus 3. Right. So let me represent this on the scale in S plane, sigma axis, j omega axis. 1, 2, 3, minus 1, minus 2, minus 3. And it is clear that pole location is at s equal to minus 3. So represented there as usual, showing a dotted line here at the pole location and marking the ROC sigma less than minus 3. Sigma less than minus 3. Now, what is the range for sigma?
Minus infinity to minus 3.
Now, does this sigma equal to 0 line is present inside the ROC?
No, sir.
Is not inside ROC. Okay. Therefore, the conclusion is this h of s 1 by s plus 3 with ROC sigma less than minus 3 is not BIBO stable. Now, let me show you one more example. H of t equal to minus e power of 2t u of minus t. Now tell me h of s transfer function for this.
1 by s minus 2.
1 by s minus 2. And what is the ROC?
Sigma less than 2.
Sigma less than 2. Okay. Now, let me again plot this. Real axis, imaginary axis. S plane 1, 2, minus 1, minus 2, 0. Pole location is at s equal to 2 here. As usual, drawing a line. Sigma less than 2 goes towards left hand side. Now tell me whether this, what is the range for sigma now?
Minus infinity to 2.
Minus infinity to 2. Now does this sigma equal to 0 line is present inside the ROC?
Yes,
Yes,
sir.
sir.
So it is inside ROC. Therefore, let's have a conclusion that h of s equal to 1 by s plus s minus 2 with ROC sigma less than 2 is BI equal stable. Okay. So like this, we can quote some examples. Just check whether imaginary axis is inside the ROC or not. And then we can have a conclusion of this. Shall I go for the last case?
Yes, sir.
Yes, sir.
Last case is both causal and BID stable. And I will directly explain this based on an example. It will be very easy for you to understand. Now I am representing s by h of s as s by s plus 1 s plus 3. Okay. And tell me the pole locations now.
S equal to minus 1 and s equal to minus 3.
S equal to minus 1 and is equal to minus 3 of the poles. And now I am directly representing some ROC geometry display. So 1, 2, and 3 all are real poles for this problem. Minus 1, minus 2, minus 3. One pole is at minus 1. One pole is at minus 3. Okay. Now what I am doing is, as per the condition for causality, how the ROC should be? Only causality. How the ROC should be? The condition for causality. How the ROC should be?
Right of rightmost.
Right of the rightmost pole. Now I am drawing the same. I am representing the ROC as right of the rightmost pole. Does the condition for causality satisfied here? Right of the rightmost pole?
Yes, sir.
Yes, condition for causality satisfied. Now please check for that in that whether the imaginary axis is included or not.
Yes, sir.
Yes. So here the ROC is right of rightmost pole, right of rightmost pole, and imaginary axis is inside ROC. Then this is the best example. The ROC which I am representing, this ROC of this system, for suppose if h of s is a system transfer function like this, and if ROC is like this, then we said that the system is both causal and stable. Now, is it clear? I will go for another example where it doesn't satisfy both. Okay?
Yes, sir.
Yes, sir.
Right. Second example. Now, I am representing some transfer function 1 by s minus and s minus 3. So, co-locations are at s equal to 2 and s equal to 3. So, negative axis is 2 and 3. Co-locations are at s equal to 2 is 1, s equal to 3 is 1. And now I am representing the ROC directly. Just I am assuming the ROC. So there is no point behind how the ROC is plotted. Just I am assuming the ROC is like this. Okay. Now tell me, among these s equal to 2 and s equal to 3 poles, which one is the right of the rightmost pole? I mean, what is the rightmost pole? Sorry.
3, sir.
3.
So s equal to 3 is the rightmost pole. And pole. And ROC, is it satisfying the condition for causality?
Yes, sir.
Yes. Now this region becomes the ROC. Now, does this ROC is including the imaginary axis?
No, sir.
No. That means this transfer function, if its ROC is like this, then that's h of s is. Tell me now, what is the conclusion from this?
It does not satisfy BI
Yeah,
stability.
it is causal. H of is causal, but it's
Not
not
stable.
BI stable. Okay. Now I will show one more example. For example, directly I will plot an ROC based on some transformation. S plus 2, S plus 3. So minus 1, minus 2, minus 3. Main axis. Main axis. Co-locations are at s equal to minus 2, s equal to minus 3 are poles. Marking the poles. And what I am doing here is just I am representing the ROC as left of the leftmost pole. Now see, is this s equal to minus 3 the leftmost pole?
Yes, sir.
Now the ROC is left of the leftmost pole. Yes?
Yes, sir.
Right. Now tell me, is this system H of S represented by these two poles and having the ROC like this? Is this system satisfying any of the two conditions? Is it causal? First tell me.
No, sir.
This transfer function is this system is not causal because here the ROC is left of the leftmost pole. So H of S is not causal. First condition satisfied. Okay, done. Now, as per the ROC I have shown, Is it satisfying BI stability?
No, sir.
No, because sigma equal to 0 line is not in the ROC. So this system is not causal and not BI stable. Okay, so this is neither causal nor stable. Okay, now last example I will show you. H of s equal to 1 by, not always 1 by, you may have some polynomial, but ROC is always defined by equals. That's why I'm not bothering about the zero locations. Or I can write s plus 1 by k, no problem. S minus 2 into s minus 3. And for this transfer function, this ROC is given, what I'm drawing now. Poles are
S equal to 2 and S equal to 3.
right, s equal to 2, s equal to 3. Now what I'm representing here, the ROC is, just assuming that the ROC is left of the leftmost pole. Now, tell me, conclusion from this. Is this system H of s with such ROC, is this system causal?
No, sir.
H of s is not causal. Okay. Now, do you observe that H of s is satisfying BI stability?
Yes, sir.
Why it is BI stable?
It contains the line sigma equal to 0.
Right. H of s is not causal, but it is BI stable. Okay. So we may have such systems. If H of s having such poles and the ROC is like this, then this is a good example for system not being causal, but it is BI stable. So I have shown you 4 examples where 4 or 5 or more than one examples, right? So here we see that, yeah, here we'll start here. So first example, we see that the ROC is right of the rightmost pole and it is including the imaginary axis. That means if the transfer function is like this and its ROC is like this, then the system is both causal and stable. This is the conclusion we have drawn. Second example, we have 2 poles for the transfer function and the rightmost pole is s equal to 3 and the ROC I have represented is right of the rightmost pole. That means this system with such ROC will be said as causal. But since imaginary axis is not included in the ROC, then the system is not BI stable. So this system is only causal, it is not stable. And third example, we have seen that for this transfer function, and if that transfer function of that system is having ROC like this, left of the leftmost pole, then here you also observe that the imaginary axis is not included in the ROC. So such a transfer function with such ROC is neither causal nor stable. And you have one more example where we observe that the leftmost pole is 2 and the ROC is left of leftmost pole. It is not satisfying the condition for causality. But since the line sigma equal to 0 is including in the ROC, then it is BI stable. So this H of s with such an ROC is a good example for system not being causal but BI stable.